particular, he will be looking at the role of nuclear energy in this transition. He's uniquely well qualified to do this. From 2009 to 2016, he was Chief Executive of the UK Atomic Energy Authority, has a lifelong interest in realizing fusion power. He's Fellow of the Royal Society, of the Royal Academy of Engineering, and in 2012 was awarded the Glazebrook Medal by the Institute of Physics. He has two major leadership roles here at the university, one right here as acting director of the Oxford Martin School, and he's also president of Corpus Christi College. And he also just completed 2 terms, I think, as a member of the Prime Minister's Council for Science and Technology. So Steve will talk to us for about 40 to 45 minutes, and then we will have time for questions, and we'll finish at 6. I just need to warn you, for the questions, we are filming this event and it's being live webcast, so do be aware of that. If you want to ask a question, you are being watched around the world. But without further ado, I'll hand over to Steve.
Thank you very much, Julian. So I have to remember not to say anything too controversial during the talk too, so there we are. The title, of course, is absolutely wrong, because I'm not sure I can really answer the question, when is the energy transition coming? And it's not really one that transition anyway, because I think it's an evolution that we're going through. And I'm not an energy economist, and I wouldn't be the right person to talk to you about all the ins and outs of the economic arguments here. I'm a scientist who spent a lot of my life worrying about energy supply, and particularly nuclear energy supply. And I'm going to focus on some of the issues to do with why I think we still need nuclear in the energy mix, although we have seen such encouraging signs in renewables that there has been a shift in the last few years in the optimism level on decarbonizing our energy. The thing I couldn't possibly do would be to take you through all the arguments why we need to decarbonize. I couldn't possibly take you through all the arguments why we need to start addressing it now. If you attend enough of these lectures, you will have seen those arguments, and I hope you are convinced that it's really important that we start reducing our emissions now, not 10 years from now, and not 20 years from now. So part of that is how do we do that? And I'm going to focus mostly on the UK because my role has been more in the policy arena, has been more in the UK's policy in energy than it has been in worrying about global energy issues. I will finish off talking about fusion because that's what I do. And I do want to give a plug for why it's very important to look at that part of the problem. I'm going to start by talking about the UK plan, which is, a sentence that has UK and plan in it. It's really worrying, but anyway. It's a very short sentence, so anyway, we're there. I think the energy problem that we're facing in the UK is really in 3 stages. I think the first stage is one that we're teetering on a bit at the moment, and that is particularly our electricity supply is just about adequate for our needs. And we're teetering on the edge of having almost zero capacity factor in our electricity supply, although some incentives have been put in place to try and alter this. We've been teetering on the edge of this for about 3 or 4 years now, and that we really have to stabilize that issue. That's not an issue about decarbonizing, and it's not an issue, it's just an issue about making sure that we have enough capacity in our system that if we have an accident in probably 2 major power stations, we will have blackouts, and that's probably too risky at this point to be in a situation like that. The second stage, which is really the 50-year timescale, is about decarbonizing our energy supply and at all costs. So here we might be looking at transitional technologies, technologies that don't really scale to the fully sustainable. They're not scalable to, centuries. They're scalable maybe to 50 years, maybe to 100 years, but will have to be replaced by more sustainable technologies in time. But they are the technologies that we can deploy now so that we can start tackling the problem now. And I look upon conventional nuclear to be one of these transitional technologies, and carbon capture and storage to be one of these transitional technologies. Then the stage 3, which is really on the centuries time scale of whatever plan you have. This is way beyond the UK plan at this point, but the stage 3 would be the sustainable technologies that we can look upon centuries and millennia in terms of their applicability to supplying us energy. And there, I think we really do have to understand how we integrate a lot of renewables and possibly a lot of advanced nuclear too. I want to address this problem, do we need nuclear? And I want to address it partly because we have such a... I came back from the US in 2008, and everybody was saying, well, we've gone back to nuclear, and we're going to build some nuclear power stations, and by 2016 we might have 4 new nuclear power stations at the 1.6 gigawatts scale. And maybe by 2020, maybe we'll have something comparable with 16 gigawatts of installed nuclear capacity. Well, between 2008 and now, we haven't really even started building one of those nuclear power stations. And the question is, do we need to? What should we do with that issue right now? We have failed politically and economically on that problem, but should we still be pursuing it? I have an answer, but maybe I'll reveal it later. Do we need nuclear, and what kind of nuclear? So actually, you can pretty much guess what the answer is because I'm going to talk about what kind of nuclear. But we'll talk about the problems that we're experiencing with the large conventional reactors. And Hinkley Point, which is supposed to be the first of the new generation of British reactors, is a poster child, really, for the problems that we're having with large conventional reactors. There's an enormous amount of excitement in the UK now, and for some time in the US, about making small modular reactors that can be manufactured rather than constructed. So they're made in factories, they're put on big trucks or railway cars, and they're shipped to the site where they're deployed so that you have construction times that are in a few years instead of construction times in a couple of decades. And whether that is a good idea, how it could be deployed, is a big question that our government is wrestling with at the moment, and there's a large consortium talking to government, led by Rolls-Royce, about whether small modular reactors are something we need to do. And then, of course, because in the long run, conventional nuclear does not scale. It doesn't scale to a sustainable source. And therefore, if we need what nuclear can deliver, which is a constant base load to your electricity supply, if we need it in the long term, then we will have to be looking at something like fusion in terms of what we deliver. So there has been progress. If you look at the last, this is 2016, this is 1970, this is 1 million tons of oil equivalent up this way, and this is coal, oil, gas, nuclear. You can see the peak of our nuclear somewhere around here, and then decreasing down this way. And wind and solar, absolutely can't see it. And now look, this is real progress we're looking at here. Bioenergy coming up here. This is wood chips and others. You can see probably the most significant thing in this picture, actually, is the decrease in coal as we come through this period. That progress has been important to us starting to look at the emissions in Britain and reducing the emissions in Britain. So that really is progress, and there is reason to be sort of, that Britain isn't ignoring some of these problems, and that the basic directives that have given rise to this are working somewhat. Now, part of the problem right now, of course, is we don't have we have almost no new plans being formulated in government in Whitehall at the moment on any of these subjects, because we're very much focused on Brexit and all the issues to do with Brexit. So we have to go back to look at the carbon plans in previous times to see what government thought we might be doing in terms of deployment towards the 2050 goal, which is an 80% reduction in greenhouse gas emission from the UK. These are model scenarios, and this was in the Department of Energy and Climate Change 2011 carbon plan. And unfortunately, it's quite difficult to read this, so I'll point out some key numbers that are here. This is basically, this is talking about what energy savings they assumed we could get per capita. So, for instance, this is 50% here, 54%, 43, 31. These are different scenarios. This is what they call the core scenario. This would be more renewables. This is more carbon capture and storage. And this is lots of nuclear right here. And the key things that we're going to be delivering, and the other part to this is that electricity demand will go up, because we're essentially using electricity to replace many other things. I kind of like wandering around waving my arms about, if that's okay. The electricity demand increase assumed in this models was 38% here, 39% here. This is the kind of thing you're doing with heating and insulation and low emission cars, etc. They're assuming we can do a fair amount of carbon capture and storage within these scenarios. Here in the electricity generation, for instance, there's 28 gigawatts. In the core scenario, there's 33 gigawatts of nuclear. We currently are at 10. 28 gigawatts of carbon capture and storage, and 45 gigawatts of renewables in that system. Right. If we look at the lots of renewables here, this is the lots of renewables one. It's 16 gigawatts of nuclear, 13 gigawatts of carbon capture and storage, and 106 gigawatts of renewables. Part of the problems with these scenarios is that there are certain technological things that would have to happen in order to make it possible, for instance, to work with 106 gigawatts of renewable capacity in this, and that probably means storage, certain kinds of backup, etc. Those are not modeled fully in the models that come out of this. But this was the kind of thing, and I did want to point out, this is the big nuclear one, 75 gigawatts of installed nuclear capacity. Now, with your nuclear, you run it probably 90% of the time, so a huge amount of your energy in this particular scenario would come from nuclear power stations. These were the scenarios that in 2011, and 2011, David Mackay, who wrote that wonderful book on sustainable energy without hot air, was the chief scientist of DEC at that time, and he was sort of supervising the modeling that went behind this. It was the time at which we were looking to try and have a strategic look at what we needed to deliver to decarbonize by that time. Within government, there's been almost none of that since then. There's been some. Within universities, there's been plenty of work like that, and it's not my expertise, so I should really not say too much. I think what was great about this, what was great about the last few years has been that the cost of renewables is starting to make an important dent. And it's 5 years ago, if you talked about offshore wind with investors in renewable energy, they would say, not touching it with a barge pole. The costs were up at about, so what you really want your costs to be, around £50 per megawatt hour. That's what you want your cost of electricity to be competitive on the market right now. The cost for renewable, for offshore wind was peaking up at sort of 130, 140 pounds per megawatt hour. That would make it extremely non-competitive in the market. And yet one of the big hopes for the UK is to deploy a lot of offshore wind in places where people don't worry so much about having something in their backyard, and in places where the wind is very consistent, so you get very little intermittency in the power generation from those. What we've seen is actual delivery of offshore wind around about 97, 100 pounds per megawatt hour. That's where we've seen delivery, but we've seen auction prices now dropping to around 57 pounds per megawatt hour. So we're seeing offshore wind catch up here. And part of that is to do with sorting out the financing, but part of that is also to do with sorting out the engineering. There was an initial phase of putting in offshore wind turbines, which, there was a lot of engineering hiccups and a lot of time taken with the maintenance and the construction, and we were learning on the job as we were putting them on. And about 5 years ago, there's a complete dip in confidence by government and by investors in that this would really work out. But fortunately, people persisted. And really, very short time later, starting to pay off. And we will be installing, I think, some tens of gigawatts more in the next 5 years, which will make a huge difference to us. So wind is coming down in price. I mean, it's amazing. I took a cruise, because I was talking about science on a cruise, and up the west coast and around the top of Scotland, and looking onshore in southern Scotland. This is the sight you see almost everywhere. This is looking across, I think, from the Forth onto the mainland, and you see these vast amount of onshore installations. The offshore installations are still coming up, and they will get more powerful. They'll get more powerful because we'll get bigger wind turbines with time, but the onshore is pretty remarkably dense at this point on the west coast. I have to thank, by the way, Cameron Hepburn for giving me slides. One of the things I think that crept up on us without really noting, when I was running the Atomic Energy Authority, we had a company on site that made crystalline silicon for solar photovoltaic cells. And unfortunately, they were essentially driven out. And they were driven out because the Chinese got into the market of making photovoltaic, silicon photovoltaics, and the price has been coming down absolutely remarkably. And they're starting to be a very cost-effective way in sunny climes to make electricity. I'm not going to belabor this point, and because I'm not an expert, and because at Oxford we have some wonderful people in solar, but this is something I think you may have seen last week, in fact. But it's about the price of solar energy, essentially, for a kilowatt hour, coming down with time. Here's 2000. I'll try that again. Here's 2050, here's 2000. Of course, it's extrapolation from here onwards. This is the price of nuclear electricity existing. This is unfortunately the price projected. Well, it's not, it's what's called the strike price, the guaranteed price of electricity coming from Hinkley Point, which will be our next, which may be our next nuclear power station. It's done it again, okay. I think one of the things here, and as a scientist, is, and we've got some marvelous work going on here in Oxford in Henry Snaith's group up in physics and his company, is that there's a lot of innovation going into the next generation of solar cells, and the efficiencies will go up. And every time the efficiency goes up, it becomes more and more cost effective to use those cells. I think the efficiencies have to go up more than the prices have to go down now, because the prices are so small that in fact really it's not the solar cell itself that's costing you money, it's all the other things that go around it. It's the aluminium frame, it's the wires that come in, it's all the other things. And so the only way we can actually drive the price a heck of a lot more down is to get more from the same area. And so these rises in efficiencies, so this is basically the efficiency in percent, and we're working around this sort of 15 to 20% efficiency with the standard installations at this point. If we can push that up by 50% or 100%, it's just a direct impact on the cost and effectiveness of photovoltaics. This is all very encouraging. 5 years ago, we didn't think like this. We didn't even think that photovoltaics would have any impact at all on the UK, and it will have some, much better in Spain, much better in Southern Europe, obviously, than in Northern Europe. And I think in Germany, sort of the analysis is probably that of the renewables, 20% might be in photovoltaics, and the rest will be in wind, in terms of a sort of optimal mix of what you might do into the future. This is again one of Cameron's slides, and I think this is a very interesting thing. We've been predicting, and I've watched this happen, that renewables will come in very slowly, and that we will have a slow turn down of oil, coal, and gas. And the fact that renewables are coming in much faster makes me very happy, because one of the things that was very worrying was we keep finding more gas, more oil, more hydrocarbons, right? And we're never going to be in that situation, which we thought maybe 40 years ago, that we would just run out of hydrocarbons before we had blown the atmosphere. But the problem now is we've got so much hydrocarbons, and nice cheap hydrocarbons, that we could go on using them essentially forever. And unless we have political agreement that we're not going to dig them out of the ground, and we're going to leave them in the ground, what we've got to do actually is we've got to make renewables ways of making energy cheaper than using the hydrocarbons. That way we don't have to rely on Mr. Trump agreeing to the Paris Accord. That way we don't have to rely on countries like Russia, etc., because people will be driven to use renewables because they're cheaper. And that would be more convenient, and I hope that some of that will happen. I think Cameron's point is that actually these predicted changes are happening much faster than anybody predicted. This is very interesting because this is the global capacity of solar photovoltaics installed in gigawatts. So just to give you a scale, a typical day on the British grid in terms will peak at around 40 gigawatts of power being delivered. We have a total installed capacity of just around 70 gigawatts. So these numbers here, this is worldwide, they're modest numbers. Right? But these were the predictions of the International Energy Agency with years. And what you see is this is what they predicted in 2006. This is what they predicted in 2008. And they were constantly following the actual line, which is this dotted line here, and adjusting upwards and upwards and upwards and upwards. There is actually, this is the physicist in me, a second derivative here, so the slope of the line seems to be actually increasing there. So probably modeling it this way is not the way to do it. But I think that's remarkable. I don't remember a technological change that caught us so much by surprise in terms of against our own predictions. Now, there are all kinds of ways in which you might say, well, when you first enter the market, you're going to take the best sites for what you're doing. When you first enter the market, you put it in the best places. All those things probably are in these figures. But I think we understand that photovoltaics are going to make a big difference to the worldwide energy problem. Probably much less to the UK. Probably much more in the line of 10, 15% in the UK. So this looks great, right? And now we're going to move forward and we're going to make, we can power our country by renewables, but we can't, actually. And we can't because renewables are not on all the time. Because photovoltaics only work in the daytime. That's one reason. They work a whole lot better in the summertime than they do in the wintertime. Because the wind is very intermittent, and we get wind power. Sometimes we will get nasty, dark Decembers with no wind power, as we did about 2 years ago, in which you just couldn't rely on renewables at all. And a nice analysis of this is given in this paper by Fritz Wagner in 2016, where he is working in Germany and concerned about the gradual erosion of what we call the baseload of the electricity system. That's the things that you can turn on and leave on. Nuclear power stations are like that. They basically operate sort of 90% of the time. And they give you a chunk of the electricity that doesn't go up and down, and you can take some of your load that way. These are 2 weeks. So what they did here is that in Germany, you can get the data from the load on the electricity system, how much demand there is, and you can get the data from the wind, and you can get the data from the photovoltaics. And so you can look in 15-minute intervals. So you can have a time series of, let's look at this week, which was the 26th week beginning the 26th of March 2012. Here's the wind, which is about 1/3 offshore, 2/3 onshore in this, etc. But what they've done here is they've scaled the actual data from 2012 so that they've pushed everything up so that the total amount of renewable energy generated in their imagined experiment is 100% of the demand of Germany. So at the moment it isn't 100%, but what they've done is they've said, let's take it and imagine that we've installed enough wind turbines and photovoltaic that we can just take the mix as we have it now and scale it up so it produces 100% of our energy, and see how we can match what we're generating with the load. And if you look in this week here, so the blue is wind, and here's obviously the middle of Monday. There's your peak sunshine during Monday, there's your peak sunshine during Tuesday, etc. So the yellow is the solar. The brown here is backup. Because here's the load, the black line here, that comes across. And at this point, early on Monday morning, we don't have enough wind, and certainly no solar, because this is the middle of the night, to supply the need, the load at that time. So we have a backup on. And the backup works there, and then when you have renewables, he imagines that you can just switch off your backup and transfer to the renewables. When the renewables are too much, he counts that as a surplus, right? But he's always got to match the line here. In this particular line in the 26th of March, the load is here, the delivery is here. You've got a lot more renewables this week than you need, because you've scaled just the total amount of energy for the year and not at any particular time during the year that it matches. If you look at this week here, which is the 12th of November on the same year, what you will see that there wasn't very much wind power and there wasn't very much solar, and during that week the backup system was matching the power. This is a well-known problem. They're nowhere near the first people to have worried about this problem, but it's an interesting analysis because you can quantify with actual data from the system as it exists how much of a problem you really have in matching this and what you would have to deliver in order to flatten out the supply so people could have that. Here's some interesting results from it. Here is 2010, this line. This is 2012, 2013, and 2015. And here is the terawatt hours, that's a measure of the energy delivered, in onshore wind, offshore wind, PV. This is the production of backup energy and the surplus. Those have to match by his assumptions at the beginning, that, because you're matching the total amount of renewables to the total amount that you need. What's interesting is, in order to be able to handle those moments when you have no renewables, you've got to put on 72 gigawatts, 73 gigawatts, 72 gigawatts, 73 gigawatts of backup power. And you're delivering quite a lot more backup energy than you've actually delivered in photovoltaic energy during that year, even though you scaled everything up that much. Understanding how we cope with that fluctuating load is a technological challenge. And doing it with backup, if we did this with a standard backup now, this would have to be something like gas turbines, would naturally produce carbon. Maybe this would be a natural way to use your carbon capture and storage for a period of time. Maybe that's what you would do with these, with these sources. I'm not as sanguine about this part of the problem as some people seem to be, but I'm not an expert on energy storage. Elon Musk is delivering to South Australia the world's biggest battery. That's what it's hailed as. It stores 129 megawatt hours. So basically 6 minutes of Dinkut power station. Battery storage for any long-term fluctuations in the grid is a long, long way from being something that we are capable of doing. For short-term storage, it's already being deployed. That's actually very short term. And maybe we'll, on the day time scale or the week time scale, be doing battery storage. But it's unlikely that we'll be doing anything over the sort of seasonal length scales, months, 6 months, a year time scale, being able to store energy that was produced in the high winds of the autumn gales for the middle of winter. Right? That will not, in my view, batteries will never scale to that kind of storage. And I think we're going to have to look at a variety of options of how we cope with that. Now, what the plan was, if we go back to that 2011 plan from the British government, which said, you know, what we're going to do is we're going to put in sort of a layered structure, some nuclear, some renewables, some carbon capture and storage. A key thing to that, in every scenario, was delivering some baseload from nuclear. It's not going to produce any CO2. It's going to be, these are very modern plants. They would produce energy quite efficiently. This is what our big white hope in nuclear is at the moment. I guess I am on air. I should be careful what I say. This is Hinkley Point. Right here, Hinkley Point B is an advanced gas-cooled reactor that's been working for some 35 years or something. It's a big workhorse of the British energy system. It's done very well. Those reactors have had life extension. They continue to deliver for us. Nuclear is 10 gigawatts out of our electrical generation, and it continues to deliver. Right here are supposed to be two new European pressurized reactors from the French company EDF and Areva. This is a design of a reactor that has yet to actually be completed in the 3 places that they've tried to complete it. One is Olkiluoto in Finland, one is Flamanville in France, and one is in China, Taishan. And we are hoping to get started on building these 2 reactors. Now, those 2 reactors will deliver 3.2 gigawatts, pretty much steady state to the British grid. It's a pretty sizable amount of our generating capacity, actually. Very important to get it. But in order to guarantee these reactors, EDF has been promised a strike price of 92.5, it's rather precise, pounds per megawatt hour. It's not a competitive price if you were just on the open market for electricity. But if you're talking about electricity that you can really rely on, perhaps it is more competitive because, in fact, it's going to provide that sort of wedge at the bottom of your generation. It's comparable with current offshore wind, but probably not future offshore wind, which is going to be less. If you actually just say, okay, let's take 3.2 gigawatts, let's say it's 90% available, how much money do you actually get from the electricity that you generate per year from this? Because they have a guaranteed price, so we can figure out what that is. And it's about 2.3 billion pounds per year. The cost of this reactor is probably 22 billion to produce these two. It's kind of hard to make money out of that. And I think that's why we're stuck, nobody wanting to move forward, EDF not wanting to move forward with that price, and we're stuck with a hole that we haven't any other plans really to fill in our generating capacity. By 2025, most of our nuclear fleet really will have reached the end of its lifetime. Most of our nuclear fleet is these advanced gas core reactors. They have had life extension and life extension and life extension. And as they do, we have turned down the wick on them. Basically, we don't run them quite at full power anymore because they're getting older, and we want to stay in a very safe condition on those reactors. And they're marvelous. They've been extraordinarily safe and good for us. But by 2025, only Sizewell B, will still be with us. So if you get started on building these reactors now, given the rate at which we build reactors, just about by 2025, you'll have 3.2 gigawatts of nuclear power coming online, just as you're losing about 8.5 gigawatts of nuclear in our scheme. Why is it so expensive? If you take the weight of a nuclear reactor and you take the amount of concrete in there, and you just built a Jaguar Land Rover that weighed that much, and you just built a motorway with that much concrete in, you'd be talking about $1 billion, $1.5 billion worth of stuff. Building nuclear reactors costs much more than the stuff that's in it. The intrinsic cost is very, very low. The cost is all in the waiting around, the licensing, the et cetera, right? It's all to do with the ways in which we keep it safe and we keep it licensed and we work with that. So people have argued that the problem is that these things are constructed on a site where you can't license them there. Now, aircraft engines are constructed in a factory. You put them on a production line. At the end of the production line, they're inspected, they're licensed, and they're put into planes and they fly. I mean, they are re-inspected in the planes, but it's not a long process. The argument is that we ought to be producing nuclear reactors like we produce aircraft engines. We ought to be producing ones that can be made in factories and transported to the site as a thing that you basically plug in. You pour a little concrete on the site, you plug this in, you link it up, and you get it online within a matter of 2, 3, 4 years from the beginning of construction until delivery of electricity. If you could do that, you cut down so much of the cost that's been in Hinkley Point. The cost in Hinkley Point is really the money sitting around for multiple years while you pay interest on it. So if you could actually make these things, if you could make essentially a factory that produces small reactors, they're called small modular reactors, you could deliver them to the site. Instead of having 2 big ones at Hinkley Point, maybe you have 20 or 15 of these. They're much safer. They're safer, smaller reactors that are intrinsically much safer because they have more surface area to volume ratio. it seems like a very good idea. And round about 2000, the US started to put lots of money through the Department of Energy into plans to build these kind of reactors. They've yet to actually make a prototype, but this is the company that they've poured some money into it, NuScale. This would actually be a 50 megawatt reactor. And NuScale have been talking to the British government about what it would take to have them deployed in Britain and sold in Britain. The excitement in Whitehall at the moment is of a consortium from Rolls-Royce. Now, Rolls make a reactor. They make a reactor for the British submarine. It's not the kind of reactor that you would put in a civilian situation, but they have the whole supply chain. So this could be an entirely British-made reactor. They have all the components, all the manufacturing capability to build all the pieces of the reactor, and they've put together a consortium and appeal to the British government that this is probably the way forward in nuclear. Now, these are very standard reactors. They are just like the sort of standard ones, the big ones, except scaled down. 220 megawatt reactors in pairs is what they're suggesting as a deployment. They have a 60-year lifetime. And they say they could deliver the first reactors by 2028. And then they would roll them off a production line, one every month or one every 2 months or something like that in order to be able to supply. And the target electricity price that they're targeting is 60 megawatt hours. I don't know if this is possible. They certainly have a plan to do it, and part of it is that unlike big reactors, you're making many of these. So you learn from the first one, you learn from the second one, you learn from the third one, and the price comes down. If you look at what's happened in photovoltaics, that learning is a crucial part of driving the cost down. It's never happened really before in nuclear, except possibly during the 1980s when France built its big nuclear fleet. They sort of built one reactor a year. It was the same people moving from site to site that build the reactors. That's pretty much the only time nuclear has made any money, was during that time. So this would be a very bold step. But we're going to have a hole in our electricity generating capability. And if we're not just going to fill it by burning more gas, we have to do something like this. There's a thing you don't often hear, and that is, it's a stopgap measure, because we don't really have enough cheap uranium to supply the world with a baseload of nuclear for more than about 100 years. It's of that order. Exactly what the number is difficult to say. You would have to go to advanced nuclear systems. I'll say a little bit about fusion because that's my thing, and I enjoy talking about it. So the ultimate way, probably the perfect way to make nuclear energy, is to do it from fusion reactions. Taking small nuclei of atoms, joining them together, and making a larger nuclei. And by far, the easiest reaction is between two isotopes. I'm going to show this first, I think. Two isotopes of hydrogen. This is deuterium. It's heavy hydrogen. Hydrogen has one proton in its nucleus. One proton plus one neutron makes deuterium. One proton plus two neutrons makes tritium. And there's a beautiful reaction that you can do between deuterium and tritium and make helium and a neutron. And this helium comes out with shed loads of energy, and so does the neutron come out with shed loads of energy. And if you take that neutron and you bombard lithium, you can make tritium, which doesn't exist in nature, and more helium. So the fuels for this way to make energy are lithium and deuterium. There is 60 billion years of deuterium in seawater, and there's 30 million years of lithium in seawater. It's 0.2 milligrams per liter of seawater, and it's efficient to separate it out for fusion, but not for batteries, as it turns out. This reaction, great, except for one thing. In order to make this reaction go, you have to ram your deuterium and tritium together at velocities of order 1,000 kilometers a second, which is equivalent to temperatures of order 200 million degrees. And so you have to create deuterium and tritium at those temperatures, hold it in some kind of containment, and allow them to bump into each other until they do these fusion reactions. Typically, your deuterium and tritium will come along, they'll glance off each other in any collision, and it's only when you hit them smack on do they get close enough that for a moment they form what we call helium-5, because it's got 5 particles in it, 2 protons, 3 neutrons, and it splits up into ordinary helium, which is helium-4, plus that neutron. When they get close enough, they repel until you get very close, and then they grab each other, and when they grab each other, they fuse, and they do this. We've known about this reaction since this guy, Mark Oliphant, in the late 1930s. We've known about this reaction. We've known it will be a great way to make energy, but it's really hard to heat anything to 200 million degrees. And we can do it now, but we can only do it in very, very large devices. So I'm going to go back to this. So the world decided about 2004 that we ought to try and actually do this to get a self-sustained fusion reaction. And they formed a consortium of countries that includes the European Union, America, Russia, South Korea, Japan, India, and one other, which I've forgotten, Japan, to build an enormous device in which you can hold deuterium and tritium in a magnetic field at 230 million degrees and cause it to fuse. And this is the device that they're building, and this is a picture from about 4 months ago. This is just the assembly hall. The actual machine is going to go here and will be, as the building's as tall as that, a phenomenal piece of equipment, and from a scientific point of view, a marvelous experiment. The hope is it'll do, let's get through that. What will it do? The hope is, so it's this, in here will be your deuterium and tritium. You hold it in great big coils made of superconducting coils. You hold this thing at some temperature like 230 million degrees, and the deuterium and the tritium make your helium and the neutron. And the hope is that we'll make half a gigawatt of fusion power. Yeah. I'm over time and I'm being signaled to. Half a gigawatt of fusion power. This would be the first time that the fusion would be self-sustaining. When the fusion produces power, it produces this helium. And the helium can self-heat the fuel. And if you self-heat the fuel, you can get it up to temperature, and then you don't have to pour in it any more heat, and it will continue to burn, just like a little star, because fusion happens in stars. And ITER is designed to do that. This is very quickly, this is a simulation of its operation, and look at the blue line here. What we do is, this is the heating power that we put on, and the fusion power, which is measured on this side, goes up to about 600 megawatts of power. At this time, we switch off the external heaters, and it continues to burn. That's like lighting a fire, taking the match away, and it continues to burn. And around the end of the 2020s, the beginning of the 2030s, that will be done. But unfortunately, this experiment's costing about 15 billion. It makes half a gigawatt of power, thermal power. So if you hooked it up to make electricity, it'll make about 200 megawatts of electricity. It's too big to be commercial power station. If we're to make fusion a possibility to actually power our homes, we've got to drive down the scale and the cost of this technology. Now, it's typical when you first introduce a technology, it's typical that it's too big, too expensive, etc. We all know that. But how are we going to get from this big clunky thing to something that actually delivers electricity that you want? Well, we've had some ideas, and I thought I would end up saying, just down the road at Culham, we're pushing on an idea to drive the cost and scale of that down to a manageable scale where we would be able to deliver to the market sometime in the second half of this century. Now, if fusion's to be needed, it's to be needed on that time scale. We don't need it now, but we do need it probably for the long-term sustainability. Here's the prototype of the machine working. You can see that this is at a temperature of about 30 million degrees. And it's actually, making that. And what was lovely about this is it starts off all kind of turbulent and messed up, and at some point, it comes into this beautiful state of being contained. That's what you need to make fusion work. You need a beautiful laminar state of the fuel, that's only deuterium in there, that will do that. So about 2009, I persuaded the British government we should try and improve on this and build a new version of this. And I thought I would close by showing you that it's opening about, where is it? Yeah, come back. There's supposed to be a, so about 2013, we began to build a machine that should get us around about 100 million degrees in a machine that's not much bigger than me. Well, it's a bit bigger than me, it has to be said. But this was the construction of the experiment, a bit speeded up. We don't work that fast. And the construction of the experiment, it is a design that may be able to get us to a burning fusion system in a machine that's not much bigger than the height of this bit of the machine, of the room. So maybe a small modular fusion reactor. This was the lid going on, sitting down on the job as it goes. That's the machine as it looks. The heating beams are being, this is the center column going inside it. This is the major driver of the magnetic field inside the system being lowered into place. And commissioning is sort of starting on the machine right now. It's a bit delayed because we had a leak, but hopefully physics results next year. We promised the European Union physics results next year. Now, will we be in the European Union next year is a big question, but that's what we promised them. I hope I've convinced you that there is work to be done, because I don't want us to be complacent about the solutions for energy. We don't have a sustainable solution yet. Maybe it's energy storage plus renewables, but I think we should be looking at the advanced nuclear solutions as part of the mix and what goes forward. All solutions must be tried. Actually, it's an existential question for us all that we solve this problem. And that's my thing, bring down the cost and scale of fusion. Thank you very much. We will try and have some gender balance in the questions too. This gentleman, I think he...
My name's David Dent. Clearly you're committed to this great big fusion adventure. Down at Hinckley there's a lot of earth scraping, but the French can't do it, and they can't do it at the price anyway. So Hinckley's probably not going to happen. Why did you say it's a high risk going for these modular small ones? It strikes me as it's a very low risk solution for the problem at the moment.
Oh, sorry, did I say it was a high? I certainly didn't mean to. No, I wanted to go for the modular ones. I think that's the. I think that's the way to make nuclear cost effective. The big ones are just out of control. Unless we can actually produce these things in a short amount of time in a manufactured way. I'm sorry if I gave you the impression that I don't. No, I absolutely think so.
Well, if they're not high risk, why can't we just build a few more AGRs? I mean, they've been a great success.
Well, one, we don't have the capability anymore, but it's a good question. People keep saying to me, well, when will rebuild Sizewell be? There are issues to do with that. The modern safety standards would make that rather difficult to, you might want to comment.
I did a documentary in 1971.
Hang on, sir. Sorry, nobody at the back can hear.
Sorry. I did a documentary on BBC One in 1971 on the disposal of nuclear waste. Would that now be something which one can do more safely? He says very carefully.
That's another one of the reasons that we shouldn't do fission for a long time, is because we will accumulate much larger masses of waste. One of the advantages of going to advanced nuclear will be essentially to remove the waste problem. I think whatever kind of nuclear we do, we need to do it in small units. The engineering of all these big units has proven really costly, etc. But I would like to see the transition from conventional nuclear, which has all the waste storage problems, to advanced nuclear, where we can get around those storage problems as soon as possible. But I see conventional nuclear as a necessary part of stage 2 of the transition. It is a transitional technology. It will help us get over the lump of decarbonizing our energy in the next 50 years. We're not ready with advanced nuclear to do that. And we're not ready with storage either.
Damon at the back.
Hi, Steve. You mentioned baseload several times, but I worry that's not the right thing to think about if we're going to deploy renewables, because if all the renewables switch off, if we have to have enough baseload capacity to supply them when they're missing, then, well, we might as well never turn them on, because we've got that baseload capacity there. And if nuclear plants can't be easily turned on and off, so they either run or they don't, at least that's my understanding. So it seems that we need things that can spin up quickly. I mean, the other transitional technology that has more of that property is gas turbines that can be spun up in half an hour, short length of time. We run them when we need them, and then we switch them off again. And then the goal is to get more storage as we to replace them through time. But I guess I just want you to sort of elaborate on the logic.
So what I didn't show was some further analysis by the group in Germany, the group in Italy, which is if you take a chunk out with a base load that's continual, it makes your storage problem or your intermittent generation problem much, much easier. So you don't intend to have a base load that is 100% of your needs, but you take out a certain amount with a base load, and then your storage plus your gas turbines or whatever your fluctuating backup source is much smaller and much less costly for the long run. And it's just, in the end, you have to do the sum and figure out what's really going to do. But my feeling is that you gain a lot by taking out maybe 25-30% as just a continual thing, and then the rest is easier to manage with your fluctuations. I think, but the other thing, and you guys know much more about this than I do, it seems to me that the other way is to have things that can take your excess electricity when you generate it, so that when you have those big surpluses, you turn on plants that make high energy cost materials, you turn on plants that make ammonia, make aluminium, those kind of things, during those times when your renewables are overproducing. But this is a whole new structure to our industrial base. And many, many industrial processes are optimized to be on all the time. And we need to think about how we optimize them for fluctuating loads. There's so much work to do here.
I promise this gentleman.
We should have some gender balance in the questions.
This lady down there.
Okay.
Nuclear fusion and carbon capture and storage are thought by many to be complete pie in the sky. Also, I'm opposed to wind turbines as a general rule. Certainly if they're on land or in sight of land, there is a danger that we industrialize our landscape and therefore lose something very, very precious.
Yeah. I think that powering our country is not without its, the downside. I don't like coal-fired power stations either. They're kind of ugly too.
on one of your initial slides, you showed the cost of fissionable nuclear energy as a sort of cluster. Do those figures take into account the decommissioning costs on those plants, or are they without those decommissioning costs factored in?
Some of them do. We now put away money, and part of the deal on new nuclear power stations is that they put away money for decommissioning. So that's part of the cost of going forward for modern plants. That little cluster on there, I'm not sure I know exactly what that data is. It would strike me that some of them probably don't have decommissioning costs in them at all. But that would be typical. Now, the cost in other countries has been considerably lower. The South Koreans are producing nuclear electricity at about £60 a megawatt hour. So, at a very competitive cost. And they're supplying the reactors for the United Arab Emirates at the moment. I think that will be an interesting. It'll be interesting to see what that actually works out in the end. They're installing, I think, 5.6 gigawatts of installed capacity for about $24 billion. Yeah.
So I'm afraid we're going to have to close now. I'm sure Steve will be here for a few more minutes if there are further questions. But before we thank Steve for one last time, I would like to draw your attention to some upcoming events. On Wednesday, staying with the theme of energy, we have at 5 o'clock in this room Professor Dieter Helm presenting his recently published independent review on the cost of energy. That's been in the media quite a lot, so many of you will be well aware of that. That promises to be a very good event, and as extra enticement will be followed by a drinks reception. The following day, we will switch topic, and you'll get a flavour of some of the other things that we're considering at the Oxford Martin School. Professor Oliver Pybus, who is director of the new Oxford Martin programme on pandemic genomics, will look at how the management of emerging infectious disease, and in particular the contribution that genomics can make to infectious disease surveillance. It's only just beginning to be appreciated by public health agencies, and his work is very much at the cutting edge of that emerging field. So that promises to be very interesting. And on the 30th of November, the following Thursday, again at 5 o'clock, we have Professor Joe Boyden, the Director of Young Lives, and Professor Sandy Fredman, Director of the Oxford Human Rights Hub, who will be talking on the future of women in Africa, with the title Production, Reproduction and Empowerment. So some very varied topics for you to consider, and we hope you will come back to hear more. But I'd like just to thank Steve for a lecture that was incredibly insightful. Your depth of knowledge was clear, but so was your passion, and even a little physics lesson which I followed. So thank you very much to Steve Cowley.